Okay, so good morning, everyone. It's nice to have Dr. Aishwarya Agrawal here with us today. Dr. Agrawal is an assistant professor in the Department of Computer Science and Operations Research at the University of Montreal. She is a Canada Cypher AITR and a core academic member of MILA Quebec AI Institute. She also spends one day a week at Google DeepMind as a research scientist from August 2019 to December 2020. Aishwarya was a full-time research scientist at DeepMind. She completed her PhD in August 2019 from Georgia Tech, working with Dhruv Batra and Devi Parikh. Her research focus is on multimedia AI research, covering a lot of domains. She's a recipient of a Canada Cypher AIT Award, a Young Alumni Excellence Award from IIT Gandhinagar, a Georgia Tech Sigma Chi Best PhD Thesis Award, a Georgia Tech College of Computing Dissertation Award, several fellowship awards from recognized institutions. She was one of the top runners of the 2019 AAAI SCM SIG Dissertation Award. She was also selected for the Rising Stars in ECS 2018. So it's nice, it's a great opportunity for us to have Dr. Agrawal with us, and I'm looking forward to hear from his presentation on visual language learning. Dr. Agrawal, the floor is yours.
Thank you. I am still audible clearly, right?
Yes, we can hear you clearly.
Okay, perfect. Thank you so much for the generous introduction. I'm really glad to speak to you. So, yeah, today I'm going to talk about the latest research from my lab, which is on the topic of advancing vision and language research. So, these are my students. We call our lab Multimodal AI Research Lab. So, all the work that I'm going to present is done by subsets of these amazing students. Okay, so let's start. Just to give you a sense for what kind of problems we look at when we talk about multimodal vision language research. So I'm going to describe some of the problems. So image captioning is one of the tasks that the vision and language community has been using to both train models and also to evaluate models. So here the task is your AI system, your AI model is given an image and it is asked to describe the image in natural language, right? So here, for example, it says a group of young people playing a game of frisbee. Another very influential task is VQA, visual question answering. And this is the problem that I worked on during my PhD. So here the idea is do question answering with systems that also understand images, right? So here given an image, the question is what is the mustache made of? And basically the idea is for the system to be able to answer questions, right? Similarly, another common task is image retrieval, where given a set of images and a natural language description, the task for the AI system is to retrieve the image that is best described by the given caption, right? So, a gray haired man in black and yellow tie. And image generation is also a very useful task where basically now we are asking the model not just to retrieve an image, but actually to generate an image from scratch, pixel by pixel, right? Following a natural language description. So these are basically, the kinds of tasks we look at in the vision and language research. And in early days of vision and language research, which was back in between like 2014 to like 2019, which is around the time I did my PhD, we used to build like specialized models for each of these tasks, right? Like so VQA would be a different model, caption would be a different model, generation would be a different model, and retrieval would be a different model. But now the landscape has changed quite a bit since the advent of bird style models and large language models, and now we are building unified models that can do all these tasks, right? So, in terms of why this kind of research is useful, so you can motivate it from application point of view. So there are many useful applications that would be facilitated when we have strong vision language models. So, for example, we can use these models to help visually impaired people. So on the right, this picture that you see here is actually a picture captured by real users, a visually impaired user, and they're asking question, what kind of wine is this? So basically, this picture is taken from this data set called VizWiz, where basically visually impaired users. So they built this app called VizWiz, which allows visually impaired users to take pictures of objects in their house and ask, like, type in the question, and this question and the image is sent to crowd workers who are sighted and who basically respond to their query. So, if you have vision and language systems, you could automate this. So you could basically use automated systems instead of using humans to answer questions. Similarly, you must have some sort of photo app in your phone. So if you have access to a system that can understand both images and language, then instead of, if you're looking for, let's say, a specific photo, then instead of scrolling through it, you can just type in the query and, your photo app will show you the photo that you're looking for. And finally, the long-term vision here is we will be able to build systems which will be grounded virtual assistants, right? So we have language assistants like Siri, Alexa, that can answer questions about world knowledge. But if these assistants don't have visual understanding, they're not situated in the same environment that we are in. So basically the hope is if we have strong vision language systems, we can basically use it to answer questions like, have you seen my keys? Have you seen my laptop charger? And so on. So the point being, there are many useful applications of these vision and language systems, right? So let me first try to give you a sense for where the field stands right now. There has been a lot of progress in vision and language research over the past decade. So here, this is a qualitative example from a model called Flamingo, which was developed by DeepMind a few years ago, and now this has been superseded by the flagship model Gemini. Right. So here, what you see is the user uploads a picture, and then the model first captions the image. So it says this is a dog, it's a white fluffy dog, and then the user keeps asking question. So what season is this? Model says it looks like a summer day. Why do you think so? Because the grass is green and the dog is not wearing a sweater. What breed is the dog? It's Samoyed. Is the dog running? No, it's sitting, and so on, right? So basically, this is already quite impressive. This example shows that the model is not only able to recognize that it is a dog, but it also has some sort of common sense knowledge, right? So what season is it? So it is able to say that it is summer day, and it is able to reason about it that it is so because perhaps the grass is green and the dog is not wearing a sweater, right? So this is already quite impressive, especially like back in 2015 and around that time when I was doing my PhD, it was hard to even just get the models understand that there is a dog in the image and the color of the dog is white, and forget about common sense knowledge. These models would not have much of a common sense knowledge. But now the state of field has changed quite a bit. Similarly, here, this is another example from DALI model, which is an image generation model. So here we are asking the model to generate images corresponding to these text descriptions. So here we see that, it can generate images of concepts that are not realistic. So, dolphin revolving around Saturn is not something that occurs naturally, but still the model is able to imagine what this would look like, right? So this is also quite impressive. So basically, overall, what I want to say is like as a whole, as a vision language research, in the vision language research community as a whole, we have made a lot of progress over the past 10 years. And we have now models which are, quite impressive, like GPT-4, Gemini, that can understand images, that can, describe images, generate images, and so on. But what I am interested particularly, and this is the research philosophy that I take in my lab as well, is what are still some of the outstanding challenges for these models, right? Like, okay, fine, we have made a lot of progress, but are these models perfect? Are we just ready to deploy these models, or are there still some fundamental shortcomings with these models? So this is what I want to focus on in my talk today. I'll focus on three particular challenges that we recently looked at in our lab. So one is this challenge of compositional and fine-grained reasoning, and I'll talk more about that in the upcoming slides. The next is how to make these models geo-diverse and how to impart cultural understanding capabilities in these models. And finally, how to build reliable and safe models. Okay, so let's look at what we mean by compositional reasoning. So here I give the model an image and I ask it to pick which caption is correct caption for this image, right? Now what you see is both of these captions have exactly the same set of words. The only difference is that the ordering of words has changed, right? Here we are saying the dog is on the left and the cat is on the right. Whereas in this caption, we are saying the dog is on the right and the cat is on the left, right? So for us humans, it is pretty clear which one is the correct caption. And here, of course, you are assuming that left and right is from users point of view. So with that, like dog is on the left and the cat is on the right, right? We don't get confused. But these models actually get confused, and their performance of, like several papers have studied this and have shown that performance of models like Clip is not much better than random chance. So 50% accuracy, right? So this is an example of lack of compositional reasoning, or you can also call it lack of fine-grained reasoning. And here, basically, by compositional reasoning, we mean that to be able to reason about the composition of words, right? So if you change the structure of the sentence, if you change the ordering of the words, the meaning changes completely, right? And our models are not very good at this level of detailed reasoning. You can also call it fine-grained reasoning in that it requires reasoning about the relative spatial location of objects and images, right? So the model needs to know that, this is the dog is on the left and the cat is on the right. So it needs to reason about the relative location, the spatial positioning of objects and images. So these are kinds of, skills that current vision and language models are not very good at. The reason, so Clip is, as you might be familiar, Clip is one of the sort of very popular model that is being used to do vision and language research, especially to extract visual representations. And as I said earlier, models like Clip are not very good at distinguishing, like finding, like, doing this classification correctly. So one reason is, you would be interested in wondering, like, why Clip doesn't perform so well. And the reason for that is basically you have to think about how Clip is trained. You have to think about the data on which Clip is trained. So Clip is usually trained on a data set like this, which you see here on the slide. So basically, it is trained on bunch of image caption pairs. And basically, the training objective for the model is to, given, let's say, an image, figure out what is the right caption. So basically, do the matching between the correct image caption pair and give a high score to that and low score to non-matching image caption pairs. But the problem is the data, in a batch when we train the model, let's say for a given image of this dog and cat, it is asked to distinguish the correct caption from an incorrect caption, but that incorrect caption is too incorrect, as in like that incorrect caption is very different from the correct caption, right? So here you see the correct caption is dog and cat playing on the grass, but the incorrect caption is a gray bear running in the woods, right? So in order to, do the task, in order to satisfy the training objective, it doesn't need to pay attention to all the details of the caption. It is enough for the model to recognize that, okay, this caption talks about dog and there is a dog in the image, whereas this other caption doesn't talk about dog, this other caption talks about bear, and there is no bear in this image. So obviously the first caption is the right caption, right? And that is enough for the model to be able to satisfy the training objective clearly. It has no incentive to, reason about compositional reasoning, fine-grained reasoning, and all of that. So here, what we did is basically in the CVPR paper that we published last year, we proposed to improve Clip's understanding of this kind of compositional reasoning. And we basically took the approach of improving the quality of the training data, but also improving the strength of the training signal by having more, fine-grained losses that we define here. So first, let's look at how we improve the quality of the training data. So what we do is basically, in addition to the positive caption, so here we have the same example image, dog and cat, and the positive caption is in dog and cat playing on the grass. Now what we do is we kind of add hard negative captions during training. So hard negative captions are generated, like in controlled ways, where the idea is we change only one aspect of the positive caption. So we take the positive caption, alter one thing in the positive caption. Either it could be, a noun, it could be a verb, it could be adjective, and that's how we get a hard negative caption. So here the hard negative caption is a bear and a cat playing on grass, right? So basically we change the word dog to bear, and now this is no longer a correct caption, but also this is no longer a very different caption to the positive caption. It is similar to the positive caption. So the model really needs to pay attention to each and every word to figure out that this is an incorrect caption, right? So this is something that was not our novelty, like other papers have done this before. Our main novelty here was to propose some, better designed loss functions. So what previous papers have shown is, yes, you can take these, augment the positive captions with hard negative captions, and you can fine tune clip model with that, and it will show improved fine-grained or compositional understanding capabilities. But what we analyzed is the representations of this positive. If you take the representation learned by clip for the positive caption and that for the hard negative caption, they're actually not very different from each other. Like if you compute the distance between these two vectors, they're actually pretty close, which suggested that this model is not learning enough of a distinction. Like it is not learning, it's not realizing that these two captions are not very similar to each other. So basically, we basically propose this additional loss function where we say that, okay, we want to additionally, in addition to the standard contrastive learning objective that CLIP has, we enforce this basically, the loss function that these two captions should be further apart from each other. And we also enforced a ranking loss where we said that, the similarity between the image and the positive caption should be greater than the similarity between the image and the hard negative caption by some minimum threshold, right? So basically, we are saying there should be at least this much gap in the similarity of the correct image caption pair and the similarity of the hard negative image caption pair. And, that should be still greater than the similarity between random caption and basically the image. So yeah, here we can look at basically the losses. So on the left, you have the standard loss. So the way CLIP works is you have your image, you have your caption, you feed it to the respective image and text encoders, you get the embeddings, and then you compute the similarity and you maximize the similarity between the positive pair and minimize the similarity between negative pairs. This is the standard CLIP's training objective. And here we just add these two additional loss functions. The first one is basically saying the similarity between the hard negative caption and the positive caption should be minimized. And the second one is saying that there should be at least a minimum gap between the positive image caption pair and hard negative image caption pair similarity. And basically, we had this, another aspect included here where we say that, in this ranking loss, there is this notion of minimum threshold, and that minimum threshold, we don't fix it. We let it dynamically evolve as training progresses. So basically, what we are saying is, as training progresses, this minimum threshold becomes larger and larger. That's how we design it. And that essentially implies that the training objective becomes more and more difficult for the model as training progresses. So basically here you see that on the left plot, as training progresses, this threshold of minimum similarity gap increases, and the loss, but still the loss still decreases for the model. So basically the task is becoming more challenging, but the model is also improving, right? So as a result, the loss is sum total is still decreasing. The loss is still decreasing. So this sort of induces a kind of curriculum learning in the model. So the model first focuses on simpler concepts, and then as training progresses, it starts learning more difficult concepts. And we showed that we improved, the performance compared to a bunch of other models at that time. So the takeaway message from here is, I wanted to show that how vision language models struggle with compositional reasoning, but generating this hard negative examples and fine tuning models is a promising direction. And in particular, we need to sometimes explicitly, by designing loss functions, explicitly encourage disparity between positive and negative representations. Otherwise, there might not be enough learning signal for the model to learn. And yeah, you can check out the paper here if you're interested. Okay, so continuing basically the same line of idea of using these hard negative captions to improve the reasoning capabilities of the model. In the next project, what we did, and this was published at NeurIPS last year, is basically say that, okay, it's very easy to generate hard negative captions because you just need to do some part of speech tagging, like identify the nouns, verbs, and then just alter it. But can you generate hard negative images, right? So for example, here, this is the positive caption, pink sheep grazing with a large crowd of people in the background. You can generate hard negative caption where you can change the color of the sheep from pink to white. But what if you could generate hard negative image, right? Can we generate an image where the sheep actually looks white in color without changing anything else? The rest of the scene should remain the same. And why might we want to do this? Because if we have these pairs of images, positive image and hard negative image, maybe that will further enhance this fine-grained reasoning capability of models like CLIP and other vision language models, right? So, but what is the challenge here? The challenge is, it's not easy to generate these altered version of images because it's very hard to make sure that you're not introducing any artifacts, and you want to do it automatically at scale, right? So you want to be able to come up with a method that can do editing on images where the editing is faithful. So you want to describe in language that I want to change from, like, the color of the sheep from pink to white, and the model should be able to faithfully do that while not changing anything else in the image. So it's not easy to generate, like there is no way to generate images like these, right? But basically, uh, but now actually the reason why we did this project last year is we can use models like diffusion models, which are, quite good in image generation, to be able to achieve this image, hard negative images. So I'll say a bit more about how we did it, but let's look at, what kind of data we built as a result of this. So we basically took images from COCO dataset, which is very complex, has a bunch of objects in it. And we did 4 types of control changes, and that's how we created these image pairs. So here you see the 2 images, and everything is same except the stereo has been changed to television, and then we have associated captions also. So we create this data set of images, image caption pair and the hard negative image caption pair, where only one thing is changing at a time. Either the object is changing, so in this case it's an object change, in this case it's an attribute change. So we are changing the black tie with silver stripes to green tie with white polka dots. Here we are changing the count of objects, so 1 toy car to 3 toy cars. And here we are changing the spatial relation between objects. So left and right, we are swapping objects, right? So these are controlled changes, and these are, we chose this specific type of changes because, as we saw before, like models are not very good at this kind of, counting, spatial reasoning, fine-grained attribute understanding, and so on. So I won't have time to go into like describe this in a lot of detail of how we generated this kind of data, but basically the idea is to use a combination of large language models and diffusion models to be able to generate these image caption pairs. So we start with a original image from some data set like COCO and a caption written by human. And then we ask a language model, large language model, to suggest like an object edit or like a counting edit. And the large language model gives us this, edited caption. And we now take the edited caption, the original image, and then ask a diffusion model to make the corresponding edit in the image. But if you just ask a diffusion model with the only image and language as input, it will not give you the kind of image you want. It tends to over edit. It tends to change other things in the image as well, which you don't want to. So you have to, so in this case what we did is we basically also segmented the object that we want to change. So here you see, like, we have basically masked out everything in the image that we do not want to change and only focus on the region that we want to change. And if you guide the model in this way by providing the segmentation mask, then it cannot do any other kind of change. Similarly, this was for object change, attribute change, for counting change, and spatial relation change. We had to make use of layout-based diffusion model, where basically the idea is the model is not directly operating in pixel space; it is operating in a layout space. So you make a layout of here is one object, here is 2 object in a blank canvas, and basically if you want to say, let's say, do counting change, add an object, then you add another bounding box and then ask the model to fill the pixels in this bounding box. So you basically have to sort of do it in a more controlled way. You can't just do it in an end-to-end way. And then we had a bunch of automatic filtering set up, like, to verify whether the edit was done faithfully or not. And we ended up like filtering out a lot of data here. And finally, for the benchmark set, we also had human verification to verify there are no artifacts and things like that. That also led to a lot of filtering of data. So overall, like, we created this data set which has around 64,000 training samples, and benchmark set which is high quality, verified by human, but it is small in number. Okay, so I'll skip this, and basically I don't have much time to describe all the results I have here, but I will just point out the key results. So the first key result is, if you take this benchmark data set and evaluate models including like GPT-4, Gemini, you see that they perform very poorly especially on spatial relation understanding. And I think this particular model with the orange bar here is GPT-4, which performs the best on spatial understanding, but the absolute performance is still quite bad, right? So there's a lot of room for improvement here. And the other thing we did is, what if you take these existing models and fine tune them on our hard negative data, where we have both image and language hard negative. We do see a lot of boost in the performance of models. So here basically the light shaded bar is the original model, and the dark shaded bar is after fine tuning, like how much you improve the performance. So, and the blue one represents clip style model, and the green one represent large language model based multimodal models. So basically, in both families of models, both the clip style model, which is a discriminative model, and a generative model, which uses large language model, in both cases, you improve its understanding of this kind of, object understanding, attribute, counting, spatial relation by fine tuning them on this data that we generated. So yeah, overall here, what we did is we proposed a controlled benchmark for evaluating this kind of understanding of model. We also proposed this pipeline through which you can generate, this fine-grained edits in images. And overall, we show that the data set we built, it really helps improve the understanding of models. And you can check out the images and the data set, and our code is here. Okay, so that was, one theme of work that we are doing in our lab, which is about improving this compositional and fine-grained understanding capabilities of vision language models. Now, the next theme is a bit different. This is about, expanding the breadth of capabilities of the model, and in particular, here we are talking about cultural understanding. So the motivation for this is basically that, the state-of-the-art models that we have now are now become, they are much better at, almost like, very good at general scene understanding. So, for example, recognizing objects, attributes. So we did see, like, they're still not very good at fine-grained understanding, but broadly speaking, models are good at recognizing objects in images, and high-level idea of like what is going on in the images. And this is the kind of research that the vision and language community has been focusing on over the past decade or so, right? And that's why we now have, like models that have, surpassed human performance on data sets like VQA, which is a data set we built when I was doing my PhD. So basically now the time is ripe to hold these models to even higher levels of standards, right? Now we are just not limited to object attribute understanding, but in particular in this project, we wanted to test these models' cultural understanding capabilities. And in particular, we want these models to be able to recognize cultures from different parts of the world, because that's how they will be globally useful. So this is an EMNLP publication last year. So here what we did is basically built a benchmark to evaluate cultural understanding capabilities of models. So let me first talk about like what is culture, and like, what counts as cultural concept. So culture is basically, multifaceted concept that includes like, understanding beliefs, practices, symbols and norms found in human society in different cultures. So here, broadly speaking, you can divide cultural concepts into two categories: visible and invisible cultural concepts. So visible concepts include, concepts like understanding, the food items in different cultures, clothing items, drinks, and different rituals and traditions in different cultures. But also you have invisible concepts, which are not just about recognizing items and images, but also reasoning about, the values associated with those, like what are the societal norms, what are the beliefs and values in different cultures, right? So, such beliefs and values are not easily captured in language, but if you have access to images, they capture manifestations of those values and beliefs, right? So here the left image you see is basically image of two Japanese people bowing to each other, and it shows the Japanese values of how people greet each other. In center, what you see is basically here what we are looking at is a norm from Korean wedding, where actually people kind of beat the feet of the groom. So they do it in a playful manner, and this is a norm in Korean weddings. And on the right, you see the beliefs from Indian culture where people, fold hands, and this is how they basically worship gods and idols in India. So basically, the point is, each culture has a different values and beliefs, and with having access to image gives us this medium to learn about those values and beliefs by looking at how it is manifested visually. So here, basically, we wanted to capture all this. We wanted to capture both cultural concepts, visible cultural concepts and invisible cultural concepts. So we decided to use this medium of visual question answering, where we collected a data set of images that captures, cultural practices and cultural items from different countries, and then we ask humans to write questions about those items and answer questions about those items, and then we can use that data set to benchmark models. So I will skip the detail about like how we collected the images, and I can answer you if you're interested later. And basically, I'll focus on how we collected questions. So in questions, we asked, you should basically, so we had to solicit annotators from different cultures. So let's say in the data set that we created, we have like representation from 10 or 11 countries. So we basically had to solicit people from these 10 or 11 cultures and then write questions that would probe the knowledge of culture for their particular culture. So basically, we said, you should ask a question about the cultural concept depicted in the image that someone from your culture will be able to answer, but someone who is not familiar with your culture will not be able to answer. So the idea was to really probe cultural understanding of images, and we had to also guide them to how to write answers. So for example, here the question is what food item is shown in the image. So we don't want people to write generic answers like Indian bread. We wanted them to write specific answers like what is the name of this item. In India we call it naan. But at the same time, we also wanted to limit the language in this data set to be English, because we wanted to disentangle cultural understanding from multilingual. So we didn't want to have like answers written in Hindi, for example, which is the language we use in India. So we had to also guide them that your answer should be written in English and you should use regional terms only if no direct English translation is available. So basically, they had a lot of effort and thought went into how to collect this data and how to collect it so that it is meaningful for evaluation. And then we this is sort of the statistics from our data where we have questions, images, and answers from 11 countries. We managed to collect 2000 questions. We actually wanted to collect many more questions, but it was very difficult to scale this up because of the limitations of we had to ask even students at Mila who are coming from different countries to annotate this, because it was not easy to get high quality annotators on platforms like Mechanical Turk. And we collected multiple answers per question so that we can check for interhuman disagreement for the answers. So yeah, here are the examples from our data set. So we have cultural concepts across 5 different dimensions: tradition, rituals, food, clothing, and drink. And these are questions from different countries. So here's an example: what are women obligated to wear? And basically, you're supposed to look at the image and then answer this question. What is the art above called? So this is an Indian art called Rangoli, and so on, right? And here we are looking at a word cloud of what are the different concepts that are present in the data set. So a bunch of clothing items from different countries, bunch of different types of drinks, food, rituals, and so on. So basically, now coming to the key question, like the whole point of doing this exercise of collecting this data was so that we could systematically evaluate current state of the art models, like to what degree they have cultural knowledge, and especially multimodal cultural knowledge, right? Like they can understand what is being depicted in the image. So here we show the performance breakdown of the GPT-4, the performance of the GPT-4 model, and here GPT-4, we're talking about GPT-4 that can understand images. So this is GPT-4V. And then we look at basically the performance breakdown across countries. So you see that for some countries it performs well. The accuracy is close to 80%, 70%, and so on. And these are mostly countries for which there is a lot of data on the internet for the model to learn from. But as when you come to countries like African Islamic countries, the performance drops quite badly. So basically, there is a huge disparity in performance across countries. And we also evaluated open source model. Like we evaluated a bunch of models, but here I'm showing you the results for the state of the art open source model, which is in turn VL. And here we see that, generally closed source model like GPT-4 perform better than open source models. But the main thing here is there is a big gap in the performance of even state-of-the-art models like GPT-4 compared to human performance. So we also, because we have multiple answers from humans, we can compute how a human would perform on this data set. And we can basically look at the gap between the best model performance and the human performance. And here we see like the gap is negative, right? So model performs worse, much worse than human performance. So even so, one interesting thing to note here is like in the previous slide, we saw that the absolute performance of GPT-4 for India is actually here 70%, but you see that still there is a big gap between human performance and model performance. So this dark red bar, so yeah, sorry, the light red bar here, the orange bar corresponds to the GPT-4, I think, and here you see like there is more than 10%, like 15% gap, right? So humans perform actually much better. So even though the absolute performance is 70%, human performance is even 15% more than that. So overall, the point is, our models are not very good in right now cultural understanding, and we need to improve that. And we also analyze like, what kind of questions they do well on and what kind of questions they don't do so well on. So basically, when the questions are about beliefs and customs, they don't do as well as they do on questions like food, clothing, and drink. And this kind of makes sense because, the other questions about food, clothing, and drink are more about just recognizing, like surface level recognition of what item this is. So models might have knowledge about that. But when you talk about like, deeper level of beliefs and customs associated with that, models are not very good at understanding that. Okay, and here you can check out all the details. Okay, so I'll take maybe like 5 more minutes and talk about the last theme that we are looking at in our lab. So we are looking at other themes as well, but these are the kinds of themes that we looked at very recently. So I decided to talk about that. So basically, so far we've talked about the accuracy, the performance of models on different kinds of dimensions like cultural understanding, fine-grained understanding. But here now I want to talk about something which is a second dimension to evaluate how good a model is beyond just looking at performance. And the dimension I want to talk about is whether models are reliable or not. So whenever you are building, let's say, a system to deploy, let's say you're building a vision language system you want to deploy for use by visually impaired users, then visually impaired users, like, it's really important that whatever prediction the model makes is a reliable prediction, right? Because the cost of making unreliable prediction is really huge. So how can we measure the reliability of models' responses? So how can we measure that given response is going to be a trustworthy response or not? So of course you can basically look at the accuracy, you can check whether this is a correct response or not. But at test time, like when you're deploying your model, like you don't have access to the ground truth, right? Like if I'm a visually impaired user, I don't have access to ground truth. So just from some other characteristics can I figure out whether this is going to be a reliable response or not. So here, to give an example, this is an image, and the question is, which person is everyone here staring at now? And the answer given by vision language model, let's say, is catcher. Now the question is, can I trust this response, right? And especially like if I'm visually impaired user, then I don't have access to the image. So yeah, is the answer reliable? So there are existing methods of estimating models, reliability, which is some methods make use of the confidence that is generated by the model. Some methods even like, prompt the model to generate to say whether I'm confident or not. But these are not well calibrated with accuracy. So it's not the case that when the model thinks it is confident, the answer is likely to be accurate. So there's a poor correlation between models' own estimate of reliability and the downstream accuracy. So in this EMNLP paper, what we proposed is basically another estimate of estimating reliability. And here, basically, the idea is, can we basically compare whether the model is consistent in its response in two different ways. So basically, we ask the model to answer this question directly, and we ask the model to answer this question via an indirect mechanism. And then we just check whether the answers generated by these two different direct mechanism and indirect mechanism are consistent with each other or not. And if they are consistent, the model is likely to be correct. And if they're inconsistent, the model is likely to be incorrect. That's the simple overall idea. Now, there are details here. So like what is this indirect mechanism? So this indirect mechanism is basically, we take the question and we ask a large language model to generate sub questions from that question. So like in order to answer the question, which person is everyone staring at, the model generates a few other questions, like what is the batter's focus on, is the umpire visible, is the catcher visible, and then we basically get answers to each of these sub questions from the same VLM whose reliability we are trying to estimate. And then we basically, we have each of these sub questions. We get the answers to each of these sub questions from the same VLM. And then we take, the history, which is basically the sub question, the sub answer, and the original question, which we are interested in answering. And we ask either a VLM or an LLM to basically compile all this information of sub question, sub answer, and generate an answer to the final question. And then basically whatever answer it generates, we look into that. So here there are two different ways of generating. Either you can use a VLM for reasoning through this sub question, sub answer, or you can use an LLM and then can generate this answer. And basically then you check whether this answer generated through the indirect reasoning mechanism matches the original answer provided by the VLM through direct answering. And if they don't match, it is likely that the original answer provided by VLM is not as reliable. So there are a lot of more details here, like what we have this two different reasoning mechanism, and we check what if it matches the answer by one reasoning mechanism but doesn't match the answer of another reasoning mechanism. And then we do another round of decomposition, but I won't have time to talk about all that. So I'll skip all those details, but basically the overall idea is to talk about, consistency between the response of the model via two different answering mechanisms. And basically we showed that yes, we do improve, now this estimate of reliability has more correlation with downstream accuracy than, other prior estimates of reliability. So basically the takeaway message from here is, measuring AI reliability is vital for secure systems, for building secure systems, but current methods have suffer from poor calibration, overconfidence, and so much. So here we proposed consistency comparison based on task decomposition for measuring answer reliability, and this enables a more accurate estimation of reliability. Okay, so I don't have much time, but just a couple of minutes to talk about one another thing we are looking at in our lab is how to reduce hallucinations in vision and language models. So, models that can, describe images, they tend to hallucinate as well. So here what you see is on the right, it is describing the, image correctly. But for the left image, it says that it is a basilica located in France, but actually it's this monument is from somewhere in Africa. So these models are not very grounded, right? Sometimes they tend to make mistakes. And again, like here, this is not going to be safe for critical applications like helping visually impaired users. So how can we mitigate hallucination in such multimodal models? So there are a bunch of existing methods try to fine-tune models on basically data which is less hallucinated, or prompt the model to generate less hallucinated response. But here what we propose is a different way of improving, and this is a test time only mechanism. So you don't need to update any parameters of the model. You take your existing multimodal large language model, which can generate a caption for an image. So here you have an image, you have a prompt, describe the image in detail, and you take the model. And basically now what we are trying to do is we sample multiple outputs from the model, and then we rank which output is going to be less likely to be hallucinated. So we build this reward models, which are essentially another vision language model, which can basically give a score for what is the degree of hallucination in a given sampled response. And we do it like, not just at the end after sampling all the responses, after sampling the full sentence, but we do it in the intermediate steps as well. So basically, overall, the idea is you can guide the decoding process of a large language, multimodal large language model by ranking its response using a reward model. So that is basically the key idea here, and we show that with this we improve the performance, we reduce hallucination, and there is another aspect of controllability here. So we actually have two reward models, one that checks for the degree of hallucination in the response and one that checks for the degree of recall. So basically you don't want a response which is less hallucinated but also very brief, like it doesn't say much about image, right? You want a response that is also long and more informative. So our method actually allows for like how much descriptive you want the response to be, which will come at the cost of more hallucination, versus how much precise you want the response to be, which will come at the cost of response being short. So you can control, basically based on your use case, you can control what kind of trade-off you want. So yeah, that's it. That was everything. Just to wrap up, talked about three different challenges here. So VLMs are still poor at compositional and fine-grained reasoning, but fine-tuning with high-quality data is promising. And yeah, explicitly encouraging disparity is good as well. The last point is something, it's related to another project that I actually didn't cover, so I'll skip that. Then I talked about cultural understanding, where basically now, the idea is we need to go beyond traditional recognition problems now that VLMs are quite strong, and evaluating cultural understanding is not easy because especially collecting data is not easy. And even though current VLMs have decent understanding for North American culture, they perform poorly for African and Asian countries. So that's not good, and there's an opportunity for us to improve that. And finally, we need to build reliable and safe models for building secure systems. And it talked about this consistency comparison technique to improve the reliability estimation of models, and this reward guided decoding technique to mitigate hallucinations in models. So yeah, that's all. Thanks. And I went over time, sorry, and happy to take questions.
Yes, thank you, Dr. Agrawal. Any questions? So I'll ask one question by the time probably there will be more. So you mentioned about your third study that there were several labeling that you performed to determining the norms and other things from the images, right? So how long did it take actually to do this manual labeling process? Like how challenging it was it?
Yeah, so it took us several months. Basically, the main time-consuming process was iterating on the instructions. So basically, it took multiple rounds of iteration to get the annotators understand what kind of questions we want. So basically, like a lot of times, what happens is they will ask you questions about culture, but the question will not require looking into the image, right? So here we wanted the questions to be grounded in images, and people tend to ask questions like, for example, like what is the most common like food that is served during this festival in this country? You can always ask a question like that, but it's not a very useful question for us because it doesn't require you to look at the image. Like LLMs can answer that without having access to image. So just iterating on that and getting the users to understand the task took us a lot of time. And the second time consuming process was like finding annotators who would do this task from different countries. Like it was very hard to get people from, let's say, African Islamic countries, because traditional platforms do not have people like representation from those countries. So just like finding resources took a lot of time, but yeah, once we were able to find the right set of annotators who understand our instruction, then it wasn't that time consuming. I think probably it took like a month after that, I'm not sure. Yeah.
Yeah, thanks for outlining this. I feel setting up the things would be much more challenging, right? Then you get the result at the end. Yeah. Any other questions from the audience? No. No? Okay, so let's thank Dr. Agrawal for a nice presentation and. Thank you. Thank you, Dr. Agarwal.